Here. All right, so up to this point we have learned how to use conversion factors to find out various numerical values that deal with chemical, not reactions, but chemical formula, all right? So up to this point, we've talked about how to do a formula mass. We talked about what the mole was. We can determine how many entities are in particular values of moles. We can use the molar mass. That kind of got rid of the need to talk about entities, so we can convert between grams and moles. And we now know how to calculate chemicals based on their formula. Also based on their formula, we can create a conversion factor that tells me how many, bromide ions are in one aluminum bromide. And that's what the test is on tomorrow. It's on how we deal with chemical formulas, all right? Chapter 5 extends this knowledge to a chemical reaction. So now we're talking about quantities in a chemical reaction. Within a chemical reaction, we have chemicals that have formulas, and therefore we'll be using many of the skills that we've already obtained while doing Chapter 4. So, if we're going to be dealing with chemical reactions, we've got to remind ourselves a little bit about what a chemical equation looks like and what all the numbers mean. First, a couple of definitions, just so that when I start talking about this stuff, you understand what we're dealing with. Quantitative analysis, that's nothing magical. You've had that term before. It means we're dealing with numbers. And in actual fact, in Chapter 4, we've been doing a lot of quantitative analysis. We even did our error analysis using this quantitative value, what happens to our numbers. The next term, stoichiometry. What a great chemistry term. Stoichio, or stoichion, comes from the Greek. It actually stands for elements. So it's the Greek word for elements. And metry means to measure. All right? Geometry, measurement of angles, etc., etc. Stoichiometry, the measurement of elements. It's the study of relationships between the quantities of reactants and products involved in a chemical reaction. When we start doing these problems, I'll call them stoichiometry problems. If you're given a problem and you're not sure what to do, and I read it to you, or we read it together, I'll say, oh, this is where you're going to do the stoichiometry. And it's going to describe a process that we do when we calculate this information. Next year in grade 12, when we are doing a mathematical problem and I need you to just figure out something like I've taught you here, I'll say, don't forget your stoichiometry, right? Remember how you do the stoichiometry. And I'll want you to think of the process that I'm showing you here today, all right? So stoichiometry goes along with this whole process that we're going to kind of come up with. Now, because we're dealing with the mathematics involved in a chemical reaction, we want to review a little bit about what is found in the balanced chemical equation. And the balanced chemical equation, short form BCE, is the starting point for all stoichiometry questions. That's where we begin. Indicates the ratio of the amounts of reactants and products taking part in a chemical reaction. We've already seen balanced chemical equations. And we already know that if I'm looking at a balanced chemical equation like this one, the 2 represents the fact that 2 molecules of hydrogen are needed to react with 1 molecule of oxygen in order to produce 2 molecules of water. And so it's like a ratio. I can say that the amount of hydrogen needed compared to the amount of oxygen is a 2-to-1 ratio. And a ratio is a fraction. And we've seen that we can use fractions as conversion factors. And so we're going to now use these coefficients, the big numbers, in their own conversion factor that's going to allow us to calculate how much of a particular chemical is needed for a reaction, or the question could ask, how much of the product is produced. And so that's what this is going to finish the procedure of making chemistry mathematical. We know how to calculate moles of a particular chemical. Now we can input that information into a chemical reaction, and we can predict how much of a product will be produced. That makes the entire thing a mathematical calculation. Now we can mathematically deal with a chemical reaction. Now I just said a moment ago that this deals with 2 molecules of hydrogen gas, 1 molecule of oxygen gas. I just said that they were actually entities. But what did we comment about entities? Why is it a pain to deal with entities? Why did we quickly come up with something else? What's wrong with dealing with entities? Yep. They're too small. We're just too tiny. So what did we do? How did we deal with the fact that we had these entities? What did we do? Yep. Yeah, we basically put them into great big piles called moles, 6.02 times 10 to the 23 entities in each one. And therefore we didn't have to count entities. We could simply count moles. Which means now when you look at a balanced chemical equation, we do not necessarily have to be dealing with 2 molecules of hydrogen gas, but it's probably more convenient to talk about 2 moles of hydrogen gas. 2 moles of hydrogen gas would fill a space, probably about a meter by a meter, 1 meter cubed. That would be about 2 moles. So we could measure that out as a large object. 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of water. So now when you think of the coefficients, don't think of them in terms of molecules, think of them in terms of moles. I've still got writing on this slide, and that's a pain. That's a big pain. You can write down the mole ratio thing. I'm going to, as I'm still making the movie, we're going to freeze this, and I am going to fix that. Okay. The mole ratio. It is essentially the conversion factor for chemical reactions. It is the next in a growing list of conversion factors that we know how to use. As we talk about solutions and chemistry that are in water, in aqueous things, we'll have some other conversion factors. But this is the conversion factor that goes with balanced chemical equations. And it is the conversion factor that goes with stoichiometry. We can easily put them together, just like if I have a formula, like aluminum bromide, I can easily take that little subscript 3, put it in the top, and say I have 3 bromide in each aluminum bromide. For the mole ratio, the numbers that we're going to use in our ratio come from the coefficients of the balanced chemical equation, which means I could have a mole ratio that relates oxygen to hydrogen. For every 1 oxygen molecule, 2 hydrogen molecules are also needed. That's a conversion factor. That will convert my hydrogen to oxygen. Now, it doesn't actually turn the hydrogen into oxygen. It converts the number for hydrogen into a number for oxygen that I need. We're figuring out the amount that's going to be needed based on this ratio. Depending on the type of question, I may need the conversion factor that has the hydrogen on the top. It depends on what I'm calculating. I could look at one that relates the hydrogen to the water. For every 2 hydrogen moles, 2 moles of water will be formed. That's a 2 to 2. When we use it in the calculation, they'll cancel away. You don't need to put them in the calculator. They'll cancel each other away, but you can write it out. And again, we could write it the other way around, depending on what the question asks. All right? Always, 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 when you create a mole ratio, on the bottom is essentially what you have. In other words, which of the elements are you starting with? What do you have? What's the number you have? And on the top, you'll put what you want. That's kind of been the way we've been doing it as well when dealing with the other ones. If I want it to become grams, I need grams on the top and I need moles on the bottom. So that's essentially the way you're going to put that mole ratio together. All right? Let's now do a handful of problems here. Now, there's the question we're going to deal with. All I want you to write is mole calculations. Just put mole calculations. And don't write what's in the box. That's just a reminder. And then you can copy the question. So just mole calculations and copy the question. Calculate the number of moles of SO3 produced when an excess of SO2 is reacted with 2.35 moles of O2. The first thing you always need when doing a stoichiometry problem is the balanced chemical equation. You need this because that's where your mole ratio comes from. So what do we always need? First, get BCE. Now for this one, it's not too bad. I give you the reactants, I give you the products, I give you the formulas, and all you have to do is put it together and balance it. But in my next examples, it's not going to be so nice. There's going to be some names instead of the formulas. So you're going to have to be able to get the formulas. Then you're going to have to complete the chemical reaction, and then you're going to have to balance it. So for many of you, a great feel of panic is going to come across, because if you can't come up with a formula and you can't balance a chemical reaction, you're stuck. You're not going to be able to do stoichiometry. So at this point, you might be thinking, well, I might as well pack it in. Well, no, that's not the case. Number one, you need to review how to get formulas and how to balance chemical equations. That's on your time, or come and ask me for some assistance once you've given it some tries and you've struggled with your work. And if you still find that it is difficult, during a test, let's say a question needs a balanced chemical equation in order to proceed, you can put up your hand and you can say, I don't know how to do the balanced chemical equation. Typically, a balanced chemical equation runs you 3 marks. So a question like this might be out of 7 marks. If I give you the balanced chemical equation, you will lose those 3 marks, and you'll only be able to get 4 out of the 7 marks. So that means you can proceed if you understand how to do conversion factors, but you will have a far diminished mark than if you truly knew how to do everything. That makes good sense. That's just the way we mark things. So please be aware, I will let you proceed, but if you don't know how to do these things, it's going to become very difficult. Could somebody please tell me what the reactants are and what the product is? Yep, what do you got, Jen? Oh, it's not a sulfite, by the way, because it doesn't have a charge. It's actually a sulfur trioxide. Just tell me the formulas. Don't worry about the names.
Okay, so the reactant is
SO2 plus O2 to get SO3, and let's balance it. So we need 2 here. We need 2 as well. Very good. So we now have our balanced chemical equation. That's the first thing, and we must have it. Now, in order to solve these problems, I'm going to set up a little bit of a scaffolding for you here to help you think it through. What I now need you to do is I need you to imagine that you've got essentially 2 lines underneath your information. And that's not too tough because most of you have lined paper, and so you've got lines underneath your information. 2 lines. So, okay, anyway. The bottom line here is going to be our mole line. Nothing but moles goes in that second line. That's where our mole information goes. In this line right here, we're going to have other units that we may encounter. Things like grams can go in there. That's a comma, by the way. And things like entities can go in there because we could have entities instead of moles. As we continue on and learn about solutions and gases, things like milliliters or liters will go in there as well. All right? So now at this point, let's take the information that we have. 2.34 moles of O2. Under the O2 in the mole line, I'm going to write 2.35. I don't know if I said 2.32. 2.35 moles, and that's of oxygen because I've wrote it right underneath it. The question asks, calculate the number of moles of SO3 produced. So under SO3, I'll put question mark moles right there. And I put it in the mole line because it's asking me for moles, and I put a question mark because that's what I'm looking for. And now I need to convert moles of O2 to moles of SO3. So this is essentially my map. I need a conversion factor that's going to convert moles of compound A into moles of compound B, and that conversion factor is the mole ratio. That's the one that we've just learned about that comes from the balanced chemical equation. It comes from the coefficients. So now we have all the information we need to get the answer. We've got our number. We're going to get the mole ratio from the BCE, from the balanced chemical equation, and we'll get our answer. And so just like any other conversion factor problem, I'm going to write down what I have, 2.35 moles of O2. Next, my map tells me I need a mole ratio. As I stated moments ago, what I have goes on the bottom, and what I want goes on the top. I have moles of O2. So I need to get information about O2. How many moles of O2 am I going to put on the bottom? Yep. Shauna? 1. Because of the coefficient right there. For every 1 O2, I'm not even going to write down moles because there's already moles there. What's going to go on the top? What do I want to find out about? Shauna? 2SO3, because that's what I want. How do I know I want it? The question asks it, and I've put a question mark moles in my mole line. That's what I'm looking to find. Well, if I do some canceling, the O2s cancel away, and I'm left with a unit of moles of SO3. That's all I need. Now I can calculate it. Moles SO3, and if you could please give me an answer, that'd be great. 2.37 times 2. Wait a minute, I think I can do this one. 4.407. Terrible, I got to think. 4.70? 4.70. I need 3 significant digits. The 2 and the 1 are whole numbers. 4.70. All right? That's the mole ratio. It's that simple. It comes from the coefficients, the big numbers, in the balanced chemical equation. What I have goes on the bottom. What I need to find about goes on the top. Let's do another example. Mm-hmm. Once you're done writing the problem, go ahead and write out the, well, what's the first thing we always need when doing a stoichiometry problem? Balanced chemical equation. Now you'll notice we're a little meaner here. You'll notice this is a little meaner in that I simply write out phosphoric acid. You got to know what phosphoric acid is. Need your periodic tables, need the back, need those ions. Phosphoric acid is related to phosphate. Ic becomes 8. I'll take them as you're finding them, just so we don't have prolonged silence on my movie. What do we have for reactants here? And those of you that always give answers, feel free to do so. We'll let those that are slackers catch up later, because I want to get through this. So what do we got? Yes, Jen, I'm waiting on you. H3PO4. NaOH. H2O. You cannot be finished, because that would mean we would have elements disappearing into the abyss. It's still not going to be balanced. You've lost phosphates. You've got sodium gone. What else do I need? There's another product there. Yeah, you can't have elements just disappear into nothingness. That would concern many people. Mr. Lavoisier would be very concerned. What do we got? Oh my goodness. Don?
Don't you have sodium phosphate?
Yeah, what's the formula?
NaPO4.
And let's cross it over.
Sorry.
It's all right.
That'd be Na3PO4.
Beautiful. We've got to put it all together, folks. This is where all of those skills that we've been doing have got to come together. Yep. It's a double displacement reaction. You got to figure that out for yourself. You bet. You got to know it's a double displacement reaction. It's a neutralization reaction. We've learned all about this. How's this going to balance? Tom, we've spent enough time on this. Balance this for us, man.
Okay, we need a 3 in front of the sodium hydroxide.
Very good.
You need, I haven't done it myself yet, so.
Oh, that's exciting.
Yeah, it's a great story. You need 3 H2O.
I need 3 water.
And you need 2 in front of the phosphoric acid. You need 2 in front of that. Oh wait, no, do you? No, you, wait, I'm not.
You better just quit.
I'm questioning myself.
Quit right hard. You're done. It's good. We're balanced there. We're balanced there. Ooh, this is going to be a fun unit for you guys. It's going to be exciting. All right. Now we proceed just like before. 2 lines. I'm not going to draw the lines this time. Where do I write my 0.76 moles? Yep, Sean? Under the phosphoric acid, 0.76 moles, leaving that top line blank. Where does my question mark go? Michaela, where does the question mark go? Under the water. Question mark. Moles. What do we call the conversion factor that goes from moles to moles? The mole ratio. Where do I get the mole ratio? The coefficients of the balanced chemical equation. We'll get that in a second. Excellent. I think we're ready to go. We have all the tools that we need. Write down what you have. 0.76 moles of H3PO4. The conversion factor I need is the mole ratio as described in the map. What I have, where does it go? On the bottom. So what am I putting on the bottom, Amber? What am I putting down here? And how many of them? Did you say 1? That's correct. 1. 1. What goes on the top? What? Shauna? 3H2O. 3H2O. That's going to cancel out my H3PO4s, and I have moles of water, which is what I wanted. And I'll take that number when you calculate it. It's looking like 2 significant digits. 2 significant digits. 2.28, which will round up to 2.3. 2.3. All right? Now, I'm not going to let you work. It says there on the slide, question sheet part A, that top part just deals with the mole ratio. But now we're going to add in some other conversion factors that you know. We're going to start with some masses, which means we're simply going to use a conversion factor that can convert mass into moles. What conversion factor converts mass into moles? Yep, Nick? Molar mass. So now we're going to just bring into some of our other conversion factors. So let's, those are the answers, by the way. That's to the top ones. We don't worry about it. Just write down gravimetric stoichiometry mass calculations. Don't write down the bullet. And then we'll do an example. I've actually got 2 more examples to do, and then I'm done. I'm letting you work. Pardon?
Like on like just this or like
Whatever you'd like. So because we're dealing with masses, the name they give it is gravimetric. Gravimetric comes from gravity, right? And gravity simply means weight. And so metric, again, weight measurement, right? So we're measuring the weights of the chemicals, and hence it's called gravimetric stoichiometry. And so we're simply going to be dealing with some masses. But we know how to convert masses into moles using the molar mass. So this is not a difficult thing to do. It's also called mass-mass calculations because we're now going to start with a mass and potentially end with a mass. So let's give you an example. Sorry, there you go. The procedure is the same. The only difference is the placement of either what we're starting with or what we're ending with. But because it involves a chemical reaction, which you need to determine by reading the question, oxygen reacts, then it's become stoichiometry, which means, what's the first thing we need? Balanced chemical equation. Got to have a balanced chemical equation or you can't solve it. You've got to know what those ratios are. What do we got? We'll take the formulas. If you don't have it balanced, we'll balance it up in a second. Yep, Shauna? H2 plus O2, we're producing H2O, very nice. Now we need it balanced. Yep, Amber? So we need 2 and 2. Excellent. Now we're ready to put in our information. Keep in mind there's 2 lines. Where am I putting the 2.5 moles? Shauna? Under the hydrogen, second row down in the mole line, right? Under the hydrogen. Beautiful. Where's my question mark going? Shauna? No. No, I'm not looking for water in this case. Amber? Yeah, under the oxygen in the first line. I'm putting question mark. What am I going to put behind it? Grams. Grams. Question mark, grams. Now, there is not a conversion factor that can go straight from moles over to grams of a different chemical. I can go from moles to grams if I know how many moles there are of that chemical, but I can't go straight over here. But what I can do is I can go across to here, to moles of this substance. How do I find the moles of a substance if I know the moles of something else? Mole ratio. When moving horizontally, always the mole ratio. Mole ratio comes from the coefficients of the balanced chemical equation. Once I have that information, I can then move up. How do I find the mass of a substance if I know the moles? Molar mass. So I'm going to write here on this arrow MM, molar mass. Well, let's gather up the conversion factors that we need. Mole ratio I can always get just by looking at the chemical equation. Molar mass, we always do that off to the side. I need a molar mass of oxygen. Again, make sure you include the units. 32 grams per 1 mole. That guides your thinking. I have all the conversion factors I need. Let's write down what we have and let's get to the end of our map. 2.5 moles H2 times. I need the mole ratio conversion factor. Somebody tell me what to put where. We've used mole ratio enough times. Amber? 2H2 on the bottom. What I have, I'm getting rid of. Yep. How many? 1O2 on the top. What does that do? That gets rid of the hydrogen. Now in my number, I have moles of oxygen. But that's not what I want. So I need my next conversion factor according to my map. And that is going to be the molar mass. We can treat the molar mass like we do the mole ratio. I need the unit that I have no use for anymore, what I have on the bottom, and I need the unit for what I want on the top. How am I putting in my molar mass? Nick? So, you're putting the 32.0 grams because I want grams on the top, and 1 mole because I have moles on the bottom. Correct. canceling out the moles, leaves me with grams of O2. And I'm running out of space here. I don't know if I can squeeze in, and I'll put an equals there. I'm going to put another equals underneath. I'll write it underneath. You've got a number, Shauna? Sorry? 80? Did you divide it by 2? You got to divide off the mole ratio. That's going to turn it into a 40. 40 to 2 significant digits, 40 grams of O2. All right? 40 grams of O2. So there you go, gravimetric stoichiometry, nothing to be afraid of. We know how to use our conversion factor, the molar mass. We're now just using it together with our mole ratio. All right? Let's now do one more where we're starting with a mass and we're ending with a mass. The whole thing. And that is going to be not number 2, number 3. Again, we'll let you write it down. Yep.
I felt like there's significant digits.
Yep.
I was so confused by the zeros. Like, how many would that be?
That would actually be 4 significant digits on the 100. And that's because if we are putting a 0.0, then you could imagine that we're using a scale that shows to 1 decimal. All right? And if we were to put something on it that read exactly to 100.0, then that means we've measured it. Right? And remember that significant digits come from measurement and from the measuring device. And so if the measuring device is precise enough to measure to 1 decimal, and we happen to get exactly 100 to 1 decimal, then we've measured all of those, and therefore they're all significant. So how do you recognize that in a question? Well, if I'm writing down a number like 100.0, then I'm wanting you to recognize they must have measured it. Because if I didn't measure it, I wouldn't have wrote it down. All right? If it was 100, then it becomes ambiguous. Then we don't know what you measured it with, right? And that's where I should use scientific notation. Like if it was 100 to 3 significant digits, I would better to write it as 1.00 times 10 to the 2, right? I'm going to try to avoid ambiguous situations for you. But that one is 4. Because I wrote it, I measured it. I didn't really measure it. I'm just stating that I've measured it. All right? All right, thanks. Okay, balanced chemical equation. Again, my movie's running a little long, so I'll take it from whoever's got it. Don't be shy. And if you're shy, I'm going to Dom. So, Dom, I hope you're ready. By the way, happy birthday, Dom.
Oh, thanks.
No problem. Are you ready to go, Dom?
I'm not too sure. This is the one on the test I got wrong, too.
Oh, that is the one. That's good. Okay, well, let's start it out anyway. Let's do it unbalanced, if you're not sure about the balancing.
All right, well, it's Fe2
Fe2O3.
plus CO.
Yep. Yep.
As products, you have just Fe
Yep.
and carbon dioxide of CO2.
Yep. Good. The way I attack something like this to balance this, I recognize the fact that all of my iron in the iron, all of the iron oxide has to be turned to iron. In other words, I've got to remove O's. I've got to take these O's away. And the thing that's going to take the O's away are the CO's. And for each O that I need to take away, I'm going to need 1 CO. And that's going to produce 1 CO2. So because there's 3 O's here, I need 3 CO's to gather up each of those O's. Now the logic becomes very simple, doesn't it? Because then that's going to produce 3 CO2s. Each CO grabs an O, becomes a CO2. The only thing that's left is the ions. And I've got 2 of them there, so that's going to be 2. So if you do an oxygen check, it's going to work. Right? Sometimes logic like that works for you when instead of just counting, you take a step back and you look at the chemicals. Anyway, let's continue. Where am I putting the 100 grams? Where am I putting the 100 grams in this question? Yep, Nick?
The first line underneath the 2 FE.
Yeah, in the first line underneath the iron. That's what I have. What am I looking for? Where am I putting my question mark? And what unit is going with it? Shauna? Yeah? So in the grams line, question mark grams. Once you have that, you use the conversion factors that you know in order to get there. I can't go straight across. I don't have a conversion factor that turns from grams of one thing to grams of another, but I can go down. That becomes moles, and what conversion factor will do that? Yep, molar mass, which means I'm going to need a molar mass of iron. I'll get that in a moment. I can move across to moles. What conversion factor is the only one that allows me to move across the mole line? Michaela? That's okay. Nick's all over it. Mole ratio, very good. Mole ratio. And I can go back up here. What conversion factor does that? What goes from moles to mass? Molar mass. Except it's a different molar mass. It's the molar mass for the stuff that's underneath it, Fe2O3. So now off to the side, go ahead and get your molar masses. We need those. And then once we have all of our conversion factors, we just have to string them together so that they get what we want. That's all we have to do. No, I need the molar mass for iron because this one is under iron. And I need the molar mass for iron 3 oxide because they're the only 2 I need to answer my questions. That's all I'm going to do. $56 grams per mole. I remember it from this morning. Pardon the scribbling on the side, but make sure you write down grams per 1 mole. That becomes important for when we use it as a conversion factor. Fe2O3. I'm going to run out of room here, so I'm going to let you guys come up with the molar mass for Fe2O3 and tell it to me because I need to squeeze in that calculation. Do you have it totaled up? Yep. Is it? Did they completely mess me up this morning?
Say if they round completely wrong.
Then they did. They probably did. So what is it? 55.8? 55.8, and I don't know if my eraser is going to work. I'm going to try to fix that. 5.8. Oh, that's just a scribble, but that's okay. Yeah, they did. And I should have known when they said it this morning. Those of you in period 2, shame on you. Should have rounded that appropriately. Yeah, once you total it up, I'll take the whole thing. 159.6. Do we have supporters on that just before I write it down? 159.6? 159.6 grams per mole. Very nice. Okay, so I'm going to write a little dividing line here so I don't run into my molar mass calculations. And now we proceed with the same logic as we've always proceeded with. That's what makes these kind of easy. Write down what we have. 100 grams of Fe. My map tells me what to use next. I'm using the molar mass for Fe. I want to get rid of grams and I want moles. The thing I have goes on the bottom and what I want to find goes on the top. So now I got to figure out how to put it in. You have an idea, Michaela? What are you suggesting?
100 grams per mole.
100 grams is the mass I'm starting with.
Okay. 2 Fe.
That's the mole ratio. I'm not there yet. I'm right here in my map. I've just wrote this down I'm right here. I'm at molar mass of iron. This is the guy you're using.
Oh, it's 50.
5.8, but where does it go? Why? You're right. Because I have grams, right? Very good. 55.8 grams for every 1 mole. I have the unit grams. I got to get rid of it. Okay. Since Michaela's doing such a great job, we're going to keep working on her here. What conversion factor am I going to use next according to my map?
Molar ratio.
Okay, the mole ratio, and it comes from the coefficients of the data. I have Fe. I got to get rid of it. What am I putting on the bottom? And what? Yeah, 2Fe. Excellent. What do I want that to become?
Mole. 1.
Nope.
0.
Nope. Mole ratio, I've got 2Fe. I need it to become this substance here. 1Fe2O3. I need the coefficients. All right. Now I'm getting close to running out of space. My Fe's are gone. My map tells me I'm using a molar mass again next, but this time it's the molar mass for this one.
So it's the 110.6 grams on the top.
Yes, I want to get grams. 159.6 grams on the top, 1 mole on the bottom. And if I cancel out that last mole, this mole and this mole are gone, and I'm left with grams of Fe2O3. And I've got everything. So I will take that answer. Oops, I want it in green. I'll take that answer when you got it, Nick. 143.0. Do we have supporters on that? 143.0 grams. Now notice though, I have 4 significant digits, 3 significant digits, 4 significant digits. So I do want to round that back to 3, and that's going to make it 143 grams of Fe2O3. All right? Because of the 3 significant digits in this mass. Sorry? I have 4 here, but I only have 3 here, and I cannot round to anything more than my least number of significant digits. Least number. Okay? Now that sheet I just handed you, the top part only deals with the mole ratio. The bottom part deals with masses and moles. If we take a look here, and there's another question there, let's not worry about it. Well, let me just go back. I'm going to bring everything back, and yeah, I'm still making a movie here. Let's bring this back up. There's the answers to the top part. I'm not going to let you write them down now. I'm just guiding the people who aren't here where they are. There's the questions to the next 3. There's the answers. And there's the answers all the way down to 10. Now, that sheet I gave you, you'll notice there are not any balanced chemical equations. And if you can't balance a chemical equation, you're going to be in rough shape. So what I've done is, on the website, all right, under homework solutions, and under here, balanced chemical equations for calculations involving balanced chemical equations, which is the sheet you have, you click on view, and I've given you all of the balanced chemical equations. So if you suck at balanced chemical equations, you can still complete this, though you still need to work on getting your balanced chemical equations, all right? So you need to work at that. So if you don't, you're at home working on it, track that down if you can't get a balanced chemical equation. Let me just stop this recorder right now because we've been going on for like an hour here.